Okay everybody, in this one we're going to be talking about electromagnetic radiation, so light and how it's made. We're going to start off by talking about transmitting and receiving EM fields using antennas, which is what this setup is. The orientation of those fields and how these antennas receive it, and the speed of the wave due to its frequency and wavelength. Alright, so remembering back to the last topic where we were talking about having charges, so positive ones and negative ones, and how these charges have electric fields moving around them. So a positive charge will have the field going out, and if I drew these further apart we'd be able to have this a little bit more obvious. So every single charge has an electric field associated with it permanently. If we make these charges move, then we've also got an associated magnetic field. If we can make these charges move backwards and forwards, oscillate, we're actually going to have a changing electric field and a changing magnetic field. So if I make this positive charge here move really fast, we can F equals QV V sine theta. We can actually sort of look at the size of the magnetic field associated with us moving. So if we get an antenna like this one here, this is going to be a conductor, so charges are free to move up and down, and we're going to have a variable potential here, so it's an alternating current, positive, negative, positive, negative, positive, negative. So if I make the bottom here positive and the top here negative, what we're going to be doing is getting the electrons in this conductor flying down the bottom, because they're attracted to the positive, they're repelled by the negative, setting up an internal electric field. Sometime shortly after we're going to swap the polarity here, so negative at the bottom, positive at the top, and that's going to make this electron whiz up and down. And this up and down motion is going to cause a variable electric field that's going to radiate outwards at the speed of light from this antenna. So we've got this alternating electric field here. Hopefully you can sort of see the link coming. When we have an electric field that oscillates, or when we have an electric field between, say, two parallel plates, it does work on these charges that makes them move. So if I was to get an electric field like this, I would actually make these electrons move up and down. So I force these electrons to move up and down, they create an electric field that propagates outwards. When it gets to a receiving antenna, what it does is actually makes the electrons in this move up and down. This moving up and down I can read as an alternating current down the bottom here. The wave is then sort of superimposed on top of that with ones and zeros and stuff now that it's digital data, and we can actually look at the oscillation at a certain frequency and gather the information from it. So here we're sending out an EM wave because we're making electrons move up and down. Here we're using that wave to make electrons move up and down, which we can then interpret. Alright, the orientation of these fields is really important. So what we talk about when we talk about the orientation or the polarity of the electromagnetic radiation is the electric field. Alright, it's just one of those conventions like the positive test charge will move away from the positive charge and move towards the negative. So we could have, come up with a different convention where we talk about the electrons moving, but that's not what happened. Similarly, we talk about the oscillation of the electric field when we talk about EM waves. And in order to have an antenna that's vertical here, send out a signal on us to receive it, what we're going to be looking at is the electrons moving up and down due to the vertical oscillation of the field. If we have our antenna orientated horizontally, what we're going to be doing is making our electrons move up and down through the width, I guess, so it'd be like going up, down in here. We're receiving the information at the end, so we're trying to receive the information at the end. Don't know if that's out of frame. We're trying to receive the information at the end, but if these electrons are moving up and down, we're not able to, because we need them to move this way and this way in order to be able to receive that signal as a current. So it's important to have your transmitting antenna and your receiving antenna in the same plane, so that we can actually pick up the radio, TV, whatever it is. So you'll note that I can't remember which way it is, let's say city TV stations are vertically polarized and the country ones might be horizontally. It's probably the other way around. It's a 50-50 here. The last part I want to talk about is V equals F lambda. So the speed of the wave is governed by its frequency and its wavelength. So for the frequency, this is how many times per second that a wave oscillates. So how many of these per second. The wavelength is from peak to peak, so it's one whole wavelength. So if we multiply the speed at which it changes, up, down, we multiply the speed at which it changes by the distance that it covers during that, we'll find out how fast it was actually going. So it's literally a distance over time type of thing. So this is measured in meters, frequency is measured in per seconds. You put them together and you get, guess what, meters per second. For light, the speed is 3 by 10 to the 8 meters per second squared. So we're looking at something. So this is considered the universal constant. So this is as fast as anything can travel. Light just happens to travel at that speed. Alright, so you will see quite often C equals F lambda, where C is 3 by 10 to the 8 meters per second. Alright, so using this information, you should be able to tell me whether a signal will be received properly, how it's actually sent and received, and also be able to manipulate this equation, to be able to determine the frequency or the wavelength or the speed of a travelling wave.